Imagine taking like a $50,000 rod of aerospace-grade titanium, clamping it into a machine, and knowing that a single microscopic vibration over the next 10 minutes could turn the entire thing into just completely worthless scrap metal.
Yeah, a total loss.
Exactly. I mean, that is the daily high-stakes reality of high-end manufacturing. When you picture a factory floor, it's so easy to just imagine raw brute power, right? Sparks flying, massive presses crushing metal, deafening noise. But the truth is, advanced manufacturing is actually an incredibly delicate dance. It's a world governed by microscopic tolerances.
It really is. I mean, the margins for error in those environments are basically zero. If a component is off by a fraction of a hair's width, an entire hydraulic system could fail.
Right.
And because the engineering tolerances are so tight, the financial margins, like the actual
Right.
profit for these fabrication shops, they're entirely dependent on how fast and how perfectly they can execute those complex cuts without destroying the raw material.
Which brings us to today. And for you listening today, whether you are, an engineering aficionado who practically dreams in CAD blueprints, or you just love a massive, elegant efficiency hack, you are going to want to hear this. Our mission for today's deep dive is exploring a stack of technical excerpts on a highly specialized industrial process called external whirling.
Yeah, and it's just a phenomenal piece of engineering. We are looking at a scenario where engineers didn't just try to build a stronger machine, but rather they completely rethought the underlying physics of a problem.
Right. They didn't just push harder.
Exactly. They took a notoriously slow, margin-killing process
Yeah.
and flipped it into a high-speed, hyper-profitable operation simply by changing their angle of attack.
Okay, let's unpack this. Because the core problem these sources highlight really revolves around traditional thread turning. So if you need to carve deep, precise threads into a long metal rod, like a heavy-duty lead screw that moves parts inside a machine, the old way of doing it is just brutal.
Oh, it is.
It's slow, it frequently ruins expensive metal shafts by bending them under pressure, and it acts as this massive bottleneck for production.
Yeah, and to understand why it's such a bottleneck, you have to look at the mechanics of traditional thread turning. It relies on a single-point tool. So if you can, picture a very sharp, very hard metal chisel.
Okay, a chisel. Got it.
The machine takes this single chisel point and slowly drags it through a rapidly spinning metal rod. But, it can't carve the whole thread at once.
Because it would just break, right?
Exactly. The pressure would be too much. So it has to make a shallow scratch, pull back, reset, adjust slightly deeper, and drag across again. Over and over, pass after pass, slowly carving out the final groove.
And every time it pulls back to reset, that is wasted time. You are basically just cutting air.
Precisely. It takes a tremendous amount of time, but external whirling throws that entire playbook out the window. External whirling is it's a high-speed machining process that uses a rotating tool head equipped with multiple tough cutting blades, and it cuts threads on the outside of a workpiece that is turning very slowly.
Okay. The massive advantage here is that this method finishes deep, complex threads in a single, continuous pass.
Wow. One pass. So instead of dragging a single chisel back and forth dozens of times, it just tears right through the full depth of the metal?
Yeah.
But wait, if we were talking about, like, aerospace titanium or hardened steel, how on earth does a machine safely tear through solid metal in one pass without just smashing into it and destroying the tool, the metal, and probably the machine itself?
That's the big question. And it all comes down to the choreography of the machine. There are 4 perfectly synchronized motions happening simultaneously.
Our emotions?
Right. And if a programmer gets even one of these slightly wrong, yes, the cutter head will violently crash into solid metal.
Yeah.
But when perfectly calibrated, it is a beautifully safe, continuous setup.
Okay, let's figure out these 4 motions, because visualizing this is key. Based on what you just said, I'm guessing the first 2 involve the spinning. They do. First, you have the cutter head itself. This is driven by an independent motor at massive speeds. It's a ring equipped with cutting teeth, and it spins very, very rapidly.
Okay, super fast cutter.
Right. Second, you have the main machine spindle holding the actual piece of metal being carved to the workpiece. And unlike traditional turning, this spindle rotates the metal very slowly. It's gently feeding the material into the path of those high-speed blades.
So fast cutter, slow metal.
Yeah.
That makes sense. The fast blades do all the work while the metal just sort of slowly presents itself to be cut. What are the other 2 motions?
The third is the axial movement. While the cutter is spinning fast and the metal is turning slowly, the entire cutter head has to move linearly down the length of the shaft, moving along the z-axis.
Right, to actually make a spiral.
Exactly. And this linear advance has to match the exact pitch of the thread you're trying to cut. If you want threads spaced a quarter inch apart, the linear movement has to sync perfectly with the rotation to achieve that exact spacing.
Okay, so it's traveling down the rod. But wait, if it's just a spinning ring traveling straight down, wouldn't the back of the cutting blades just smash right into the walls of the thread it just created a second ago?
That is exactly what would happen, yes. And that is why the fourth motion is arguably the most critical. The entire tool head tilts.
Ah.
It has to pivot on an angle to perfectly match the thread's helix angle. So by tilting the spinning disc to align with the spiral path of the thread, the blades can carve the metal and cleanly exit without their trailing edges colliding with the freshly cut walls.
Man, that is a lot of moving parts to track at once. To help you listening visualize this, let's step away from the heavy machinery for a second. Imagine an automated apple peeler, the kind you might clamp to a kitchen counter, but heavily modified.
An automated apple peeler.
Hear me out. Instead of spinning the apple incredibly fast against a fixed stationary blade, which is basically how traditional turning works, right? You spin the apple very, very slowly. Meanwhile, you have this miniature high-speed buzzsaw hovering right against the skin. As the apple slowly turns, that little buzzsaw spins frantically, moving down the length of the apple to create a spiral and tilting at just the perfect angle so the back of the saw doesn't accidentally chop into the food it just bypassed.
You know, geometrically speaking, that is a surprisingly accurate way to picture it.
Thank you.
The slow rotation of the core material feeding into a high-speed spinning ring of blades. What's fascinating here is the structural layout of that buzzsaw cutter head.
Because it's not actually an enclosed solid ring that the rod has to thread through, right? It's more of an open layout.
That's right. The tool head looks somewhat like a thick, hollowed-out saw blade with several tough cutting inserts sitting on the inner edge of that open ring.
No.
But importantly, the tool stays completely on the outside of the workpiece.
Oh, I see.
Yeah, the metal rod isn't being shoved through a tiny restrictive hole. Because it's an open, external approach, there is no size limit imposed by a small inner ring. That structural freedom means these machines can easily be scaled to cut extremely large diameter screws.
Well, that flexibility is huge. But as elegant as the apple peeler analogy sounds, I'm guessing you can't just throw any random chunk of metal in there. If you force the wrong machine to cut the wrong material, you are guaranteeing total failure. So who are the ideal candidates for this? What specific shapes actually survive this process?
The geometric parameters are pretty non-negotiable. The part must be cylindrical. Because you're dealing with tremendous cutting forces, both ends of the metal workpiece need incredibly strong clamping to keep them from just flying out of the machine.
Right, that sounds dangerous.
Extremely. You need a chuck, which is a heavy-duty industrial clamp gripping one end, and a tailstock center, which is basically a heavy stabilizing, pin pressing firmly into the other end.
So if a factory is trying to thread a part that has a really thin, fragile profile or some strange asymmetrical shape,
they won't survive. The heavy, continuous cutting process will snap a thin rod or tear an asymmetrical piece right out of the clamps. Furthermore, this process is purely for external threads. If you need internal threads, like the spiral grooves on the inside of a heavy bolt nut, that requires completely different internal equipment.
makes sense. What about the size range?
As for the sweet spot in terms of size, external whirling is highly efficient for medium to large diameters, specifically ranging from 6 millimeters all the way up to a massive 450 millimeters.
Okay, I have to challenge something here because the physics aren't quite adding up for me.
Yeah.
You mentioned earlier that it's doing this full depth cut in a single pass.
Yes.
And the sources point out that this works on hardened steel, titanium, and high temperature alloys. If you are taking a blade and blasting it through heavily heat-treated steel in one single aggressive pass, wouldn't that immediately dull, melt, or just completely shatter the cutting tool?
It's a vital question. I mean, if you tried that with a traditional single-point turning tool, it would be instantly destroyed by the sheer density of those hard metals. But external whirling machines utilize specialized cutting inserts made of PCBN.
Okay, what does PCBN stand for?
Polycrystalline cubic boron nitride.
Wow, that's a mouthful.
Yeah, it's a highly engineered synthetic supermaterial that can effortlessly process metals up to an HRC65 hardness.
Okay, for those not intimately familiar with metallurgy, HRC65 on the Rockwell hardness scale is practically tool steel, We're
Right.
talking about metals that have been quenched and heat treated specifically so they won't be cut or deformed.
Exactly. It's incredibly tough stuff. But the reason the tool survives isn't purely because of the PCB and material itself. The survival of the tool also comes down to the machine's open design.
How so?
Because of that open cutting area we discussed, the fact that the spinning cutter is situated on the outside of the rod engineers can pour a heavy, continuous deluge of liquid coolant directly onto the blades and the metal chips as they fly off. Oh! So the heat never even has a chance to build up and melt the cutting edge.
Right. It prevents thermal overload, so you end up getting excellent prolonged tool life, even when you are mass-producing components out of notoriously stubborn materials, like stainless steel or, aerospace titanium alloys.
Which explains why the sources list such critical heavy-duty components as the ideal candidates. We are talking about things like lead screws for heavy machinery, hydraulic valve spools where a leak could be catastrophic, and even bone screws.
Yeah, medical implants are a fascinating use case.
Yeah.
Bone screws require very deep, very aggressive thread profiles so they can securely grip into porous human bone.
Ugh, just thinking about that makes me wince.
I know, right? And they're almost always made of tough, biocompatible titanium. External whirling is uniquely suited for that level of high-efficiency, zero-defect mass production. Okay, so we have a machine that can flawlessly carve titanium bone screws and hardened steel. That is incredible engineering. But engineering perfection doesn't automatically equal factory adoption. These computer-controlled machining robots, CNC machines, they are incredibly expensive. How does a factory manager justify the massive upfront cost to bring external whirling onto their floor?
The justification comes down to two factors that completely alter the economic model of a factory: mind-boggling speed and a massive leap in surface quality.
Let's look at the speed first.
Sure. So we talked about how traditional turning wastes time dragging a single tool back and forth, resetting over and over. With external whirling, because you have a multi-blade cutter spinning incredibly fast, you hit cutting speeds of up to 400 meters per minute.
Wait, 400 meters of cutting edge slicing through metal every 60 seconds?
Yeah, and those cutter spindle speeds range from 2,000 to 5,000 revolutions per minute. Because the high-speed blades carve the entire final thread profile in exactly one continuous pass, the total machining time plummets. It drops to just 1/5 of the time required by traditional methods.
So it's up to 14 times faster. That is wild. You are literally multiplying a factory's production capacity without needing to add more floor space or hire more operators.
Yes, it's a huge financial win. But like I said, speed is only half the equation. The second factor is the quality of the finish.
Okay, here's where it gets really interesting.
Yeah.
Because usually in manufacturing and in daily life, honestly, speed comes at the direct cost of quality. If you rush a job, you generally get a sloppy, rough result. But the sources highlight that external whirling actually improves the physical quality of the cut metal.
It does, and it comes down to how the tool physically engages with the metal to eliminate vibration. In machining, bad vibrations create microscopic, ugly, rough marks on the surface of the cut metal. The industry term for this is chatter. Right. In traditional turning, you have one single point of contact taking the entire force of the cut. That single chisel naturally wants to bounce and vibrate against the hard metal.
It's like trying to drag a heavy wooden chair across a hardwood floor. It catches, stutters, and jumps.
That stuttering is chatter. It acts almost like a tuning fork, sending resonance right into the metal. But external whirling uses indexable carbide inserts that provide continuous multi-edge cutting. You have several blades mounted on that spinning ring.
Okay.
As one blade exits the metal, another blade is already entering. This intermittent sweeping action distributes the cutting force perfectly and evenly across the tool head. The load remains entirely constant.
So because there's no single point taking all the stress, there's no stuttering.
Almost zero machine chatter. The uniform forces stabilize the entire process to the point where it leaves behind a mirror-like surface finish. The sources note a surface roughness that stays perfectly stable at right 0.8 micrometers.
Okay, let's break that down. For anyone not steeped in metrology, what does an RANO 0.8 finish actually mean in practical terms? Why does it matter?
Well, RAS stands for roughness average, which measures the microscopic peaks and valleys left on the surface. And RAV 0.8 micrometers means the precision levels jump up by 2 full grades compared to standard turning. It is an incredibly smooth, highly precise surface.
Wow.
And that matters immensely. Think back to those titanium bone screws. If an implant has a rough surface with microcrevices, it can harbor bacteria or create friction that irritates human tissue.
Oh, that makes total sense.
Yeah, or for hydraulic valve spools, a rough surface means hydraulic fluid will leak out under high pressure. RARO point 8 ensures a flawless seal and a sterile implant.
And there's another detail the sources mentioned that contributes to that flawless finish, right? Chip control.
Hmm.
When those blades carve out the metal, they don't just leave dust. They create distinct, crescent-shaped metal chips.
Yes, and chip removal is absolutely vital. If a tiny piece of hot, freshly cut metal sticks to the sharp edge of the blade, it'll get dragged back around and gouge that pristine raw point 0.8 surface on the next rotation.
Yikes.
But because the cutter head is spinning at thousands of RPMs, massive centrifugal force acts like a slingshot, throwing those crescent chips away from the cut instantly.
Plus, the open design allows them to use compressed air jets to blast the chips out of the cutting zone the second they form.
Exactly. The combination of centrifugal force and air blasts ensures the cutting zone stays clean, protecting that mirror finish.
Okay, I follow the mechanics of the finish, but this brings up a glaring physical contradiction. The whole mission of this deep dive is understanding the underlying physics, and something here feels off. We are talking about blasting through hardened steel up to 14 times faster, taking the entire depth of the thread in a single pass.
Right.
Shouldn't the sheer violent physical force of that massive cut push a long, slender metal rod completely out of shape? I mean, if I push hard against the middle of a stick, it bends.
It's the most logical assumption to make. Cutting long, slender metal rods historically causes severe bending problems, and a bent lead screw will absolutely ruin an expensive mechanical assembly, causing the entire machine it's installed in to bind up and fail.
Right. So how does a significantly more aggressive, faster cut somehow manage to keep the metal part straighter?
It's a brilliant pivot in engineering. It is not about the total amount of force applied. It is entirely about the direction of the force. This is the fundamental physical difference between the old way and the new way. Traditional turning pushes a single tool straight into the side of the spinning metal rod. That creates a vertical radial force.
Just taking a hammer and pushing it straight into the side of the shaft?
Exactly. It pushes into the core. And a long rod is naturally going to bow and bend under that heavy side pressure.
Okay, let me try to map this out for you listening. Think about radial versus tangential force. Like, the traditional turning is like trying to push a tall stack of wooden blocks from the side. You apply radial force, pressing directly into the side of the stack, and the whole thing immediately wants to bow outward and tip over.
That's radial force in a nutshell. It pushes the center of mass.
But external whirling is different. The rotating disc is spinning around the outside, parallel to the surface. So it's like taking a very sharp, long blade and gently shaving the side of that stack of wooden blocks from the top down. You are slicing rapidly along the edge of the blocks, not pushing inward into their core.
That is the exact mechanism. External whirling uses tangential cutting forces rather than heavy radial pushing forces. The rotating blades apply force tangentially along the tangent line of the cylinder surface.
Yeah.
The blades slice the outer layer of metal away instead of pushing against the core structure, and this slicing action massively reduces the risk of the workpiece bending or warping under pressure.
It really is all about the geometry of the angles. Instead of a blunt, destructive push, it's a high-speed parallel slice.
Yep. And if we connect this to the bigger picture, it's also about heat management. Heat destroys a metal rod's straightness just as quickly as physical pressure does. Single-point tools generate massive localized heat in one tiny spot.
Yay.
That extreme heat causes thermal expansion on one side of the rod, which physically warps and bends the shaft.
But because external whirling has multiple cutting edges taking turns in the metal,
They share the workload, so no single blade overheats. And more importantly, all that heat is transferred directly into those crescent-shaped metal chips. When the centrifugal force throws the chips away instantly, it throws the heat away with them.
oh wow.
So the overall temperature of the long shaft remains very low, which means you eliminate thermal deformation from the inside out.
But, I mean, I'm guessing there's a limit to this magic, right? You can't just suspend a 10-foot-long skinny rod of steel in the air, attach it at the ends, and expect it to stay perfectly straight just because you're slicing tangentially.
Right. Oh, definitely not. The whirling process is brilliant, but it cannot defeat the fundamental laws of physics completely. Gravity still exists.
Right, gravity always wins.
Centrifugal force from the rod's own slow rotation still exists too. So for shafts with massive length to diameter ratios, really long, thin rods, they will naturally sag and bend just from their own weight hanging unsupported in the machine.
So what is the workaround for factories cutting massive parts?
Proper mechanical support remains strictly necessary. The sources emphasize that shops must still employ hydraulic steady rests or follow rests.
What are those?
They're essentially stabilizing mechanical arms that clamp gently along the middle length of the shaft to prevent gravity and rotation from creating wild bending forces. The tangential slicing solves the cutting pressure problem, sure, but engineers still need robust support systems to manage the environmental physics of a heavy, hanging object.
Synthesizing everything we've gone through today, the core aha moment of this deep dive is really that profound shift in the angle of attack. By stepping back and moving from a blunt radial pushing force to a high-speed tangential slicing motion, manufacturers have completely transformed how they work.
Absolutely.
They eliminate the chatter that ruins finishes. They achieve pristine row-point-8 surfaces suitable for medical implants. They slice through incredibly hard alloys up to HRC 65 without melting their tools, and they do it up to 14 times faster than before.
It's a true paradigm-shifting upgrade. Going from a slow, multi-pass drag to a high-speed single-pass slice completely rewrites the economic reality of a factory floor.
So what does this all mean for you listening? I think the most compelling takeaway is that true innovation often isn't about just trying harder or building a heavier machine or pushing with more brute force. Sometimes the ultimate solution is completely changing your geometry.
It is a powerful lesson, and it leaves us with an interesting thought to walk away with. If a simple geometric shift moving from a radial pushing force to a tangential slicing force can revolutionize the way we cut the hardest steels on Earth, where else in our modern engineering, or even in our daily personal problem solving, are we stubbornly hammering away at the center of an obstacle when we should really be looking for a way to simply slice along its edge?